Christina Serpa has a degree in applied mathematics, fundamental applications, a master's and PhD in mathematics in the area of mathematical analysis from the Faculty of Sciences of the University of Lisbon. She is an invited assistant professor in the mathematics department of the Instituto Superior de Lisboa in Lisbon, and her teaching duties are usually focused on calculus curricular units for engineering. She is an integrated member of CMAFCIO, Center for Mathematics, Fundamental Applications and Operation Research of the University of Lisbon, and collaborates with the Portuguese Mathematical Society. She does research on fractals, both at fundamental theoretical level and in the context of their applications. She created the fractal regression method, having developed corresponding software to obtain fractal functions from real data. So today she will going to talk about viscous fractals as domains of fractal function. So
First of all, I will thank to the faculty members, the members of university here from the Velori Institute of Technology. I would like to address my thanks to inviting me to come here and the welcome that they provide me. You don't hear? This is on. Okay. The work I'm presenting here is a joint work with my previous PhD advisor, Jorge Buesco, and with a student of ours, is Guilherme Velez. I'm doing this work in Lisbon, and we submitted this as a paper to a journal. Well, fractal functions, I call them fractal functions. Normally in the literature they are calling fractal interpolation function because Barnes invented this term to interpolate real data and to do a way to understand data from a fractal perspective. In recent days, I took these functions, these fractal functions, and to approximate data, I created a new method, is a fractal regression method, also with the same kind of functions. These functions are solutions of a type of system of iterative functional equations, and the new thing in this regression is that it can, it may understand what is the particular properties of self-similarity in the data. And it can also estimate the Hausdorff dimension. Okay. Theoretical formulations, constructive solutions, and lots of theoretical developments are in the literature. I did the research for the most general cases, nonlinear, non-affine, for this type of equations and systems, and the results are wide. And I also understand that for this kind of systems, there was some compatibility conditions that should be verified for that we could have a solution. That solution could be. Then these compatibility conditions are also in a paper where there is a need to to have these compatibility conditions means that in between each two equations, if you have one image from one equation, it must be also coherent with the other equation. Okay, I explore more in deeply the doubly affine case. It means that in one coordinate it is affine, and in the other coordinate it will be affine. I will specify. Okay. Normally, the domain for this kind of functions are represented in P representation digits. And now I will generalize these for Vixed fractals. I will tell you what are these. These are like Cantor-like sets, and they can be constructed in multiple dimensions, similarly to this third Cantor set. These kind of fractals have a natural representation in a D tensor, also, depending on the dimensional D, and we may take consecutive Kronecker products of this tensor with itself. Here I show you how various steps the construct of Vixed fractals, and this is also nice to have computational properties. Here the goal is to apply some results from the systems of iterative functional equations now with domains that are Vixed fractals. Okay. What are Vixed fractals? The first example is the Cantor set. We have a set that is a line in between 0 and 1. We divide the line in 3. The middle is removed. This means that we end up in the first place with two subintervals. The middle interval corresponds to the digit 1, and in terms of the third representation of numbers, we have no digit 1, only digit 0 and 2. And if you apply consecutively, iteratively, this procedure, we have a set of a number of infinite numbers, infinite set of numbers. The resulting set is non-empty, compact, perfect, and totally disconnect, meaning that each pair of points has no path connecting them within the set. This is a set of points, okay, non-dense, but there is an infinite set, okay? We may generalize this construction to a uniform partition of the 0-1 interval in P subintervals of lengths P over 1 over P, and choosing which one should remove every step. This means that if you have, for instance, the decimal representation, we may choose to some digits, 2, 3, and 4, for instance, and we only have numbers that have not these integers. And when we represent the same object, we draw again the interval, unit interval between 0, 1, 1, and remove those digits, and then the remaining subintervals we do the same. Okay. The resulting set will, irrespective of the choice of the P, will be topological equivalent to the middle third Canton set, size all metric, compact, perfect, and totally disconnected set are homeomorphic. Are homeomorphic in terms of topology, not in terms of our equations. Our equations need some representation of the domain. The domain is very important how to translate these in terms of the images. The images are always obtained by its representation of the domain. Let's see how to set up these Vixed fractals. We have, for instance, an integer p that must be over 2 or over 2. We represent n2 the numbers, natural numbers that are at least 2. And we have a set of digits between 0 and p minus 1. Okay? If you have the decimal representation, p, it will be 10, and the digits will be between 0 and 9. Okay? Now, we consider the iterator function systems, fk, that is given by this expression. This gives the p representation of numbers. Each of these functions will be an element of a family that is called iteration function systems, and this function is contractive because 1 over p is less than 1. Okay, and this contraction will transform the interval 0, 1 to 1 over p sized interval from k over p to k plus 1 over p. And in the case S equal to all the symbols, the family of partitions the unit interval into this union. It means if I have all the digits, then the interval will be partitioned in p subintervals. When S is a proper subtest of this set of digits, it means that some digits are removed, then each subinterval is removed from which k is not belongs to S, and for each S in this case there is an attractor for these iterative function systems, such that this attractor equals to the union of the images of each function of the IFS. This is how to obtain attractors from the iteration function systems that will be our domains. Okay, this is for the most basic formulation. This is like Cantor set formulation. Okay. Okay, let's see here. We have the full interval. Here the subinterval 0, subinterval 2, and so on. Okay, this is the most basic 3 representation of the 0-1 interval. For the trivial case of this iteration function system, the middle third Cantor set is when p is equal 3 and S is equal 0, 1, 0, 2. The 1 is removed here. The 1 is removed because here in the middle, here, we remove this. Okay? Now we extend for more general Vixed fractals. We have D. This is the integer dimension of the space where we define the Vixed fractals. And we have, instead of 1p, we have a vector of p's. It means that for each dimension, I have 1p, p1, p2, pd, in this n2 over p. For each I have a set of digits, okay? And S will be a subset of this set of digits. Each P1 and PD will have a set of digits, okay? I have the S must be at least two elements, okay? And we now define an iteration function systems where now instead of having a function that has an index that is a scalar, now the index is a vector, okay? Is a vector that has the elements, okay? Here fk, this k means the elements and is from also a vector with the coordinates. Now we define, instead of one coordinate, remember that the basic iteration function system will be x plus k over p. Now we have a vector of the same kind of iteration function systems, and each coordinate could be thought as the previous iteration function systems, okay? The x is a d-dimensional vector, and each coordinate belongs to this 0, 1 interval. Then we may define a d-dimensional Vic-sect fractal, or d Vic-sect fractal, as the attractor of a d-dimensional IFS, that this is this set, okay? This is the main definition for the d Vic-sect fractal. D is the entire dimension where the Vic-sect fractal is defined. But the fractal dimension of this fractal is less than this, okay? Now, to construct the Vic-sect fractals, we have for each p, vector p and s, with a sequence psi on s infinitive, we have this limit. This limit means that when I want to find a specific point belonging to the Vic-sect fractal, this point will be defined as a limit of these functions belonging to the iteration function systems that belongs to the attractor, to the iteration function systems of the Vic-sect fractal, okay? And this is the definition for each point on the Vic-sect fractal. In the case of one-dimensional, we would have only this p representation, one coordinate p representation. Here, the limit does not depend on x because this is a contractive set of functions. This is a composition of contractive functions in a complete space, metric space. This is a representation of any point in a general d Vic-sect fractal, and it depends only on its pi representation. Okay. Okay. For some computations, it is sometimes useful to have this kind of iteration function systems in a matricial form. This is the matricial form where here is this case is a vector. We have the dp components here, and we multiply by x1. No, this is wrong. This should be x1, x2, xd. Also here. This is some mistake, okay? It should be x1 plus k1, x2 plus k2, and so on, xd plus kd, okay? And in the matricial form, we also may write this as d index p over minus 1 times x plus k transposed. Okay, p is the diagonal matrix P and diagonal P1 PD. Okay, this diagonal is with the inverses of the p's. Let's start with the two-dimensional Vixet fractal. Two-dimensional, I mean that this fractal is inside the two-dimensional space. It will be less than two-dimensional in terms of Hausdorff dimension. Okay. This is the first example where a two Vixet fractal. This is the attractor of this IFS. We may see here the F00 is here the case R0. It means that I only see the first. This here correspond to maintaining this square. Okay. The second one is 2, 0. It means that I stay with this part of this square. This is x1 plus 2, x2 plus 0. This is the second square that I maintain. And f11, here x1 plus 1, x2 plus 1, I will remain with this square. And 0, 2, it means that I will stay with this square, x1 plus 0, x2 plus 2. Okay? And in the last one, 2 is x1 plus 2 and x2 plus 2. I will remain of this one. This drawing is only the first step for the Vixet fractal. The next step will be to repeat, to compose this function again to the points here. Which means that this first configuration will be repeated in each square that is here. We remove these empty spaces from the drawing. Okay? Let's see another example. Here, this is another Vixet fractal. This is not the Vixet fractal. This is the first step of the Vixet construction fractal. Okay? Here we have 1, 0, 1, 0, 1, 0 here. We maintain this one. 0, 1, we maintain 0, 1 here. We maintain 1, 1 also. This is the middle square. We maintain the 2, 1, 2, 1 we maintain here. And here we maintain here. We remove all these sides blocks. Okay? And then to construct this Vixet fractal, we repeat this original cross configuration in each square here. Okay, some people say that this is a cross fractal, okay, also. Now, if you want to go to a three-dimensional Vic-sect fractal, we may start with this kind of cube. We remove the central cubes, okay, and we have this kind of attractor. This is not a tube. This is a 3 Vic-set. This is another mistake here. This is a 3 Vic-s fractal. That is the attractor of this function. This is also an iterator function system with its three-dimensional coordinates, and we define every function of this type, but we remove those functions that have the first and the second coordinate equal 1, the first and the third coordinate equals 1, or the second and the third coordinate equal 1. Okay? Here we have alls from the top to the end, from this side to the end, and from this side to the end. Okay? And we may define more with more dimensional, but in this case we could not draw it. Okay? I only draw up to 3 Vic-sect fractal dimension. Okay, this is one-dimensional fractal. I just don't need anymore to tell you how to do it because it was in the first one. And here I have the 1, 2, 3, 4 steps for each of the Vic-sect fractal I defined in the beginning. Okay. For this, I repeat this configuration in these squares and have this. Now I repeat this configuration in these squares and I obtain this. Okay. And then I will repeat this in each of these squares and I have this. Okay. With only 4 steps, we have an already very detailed object here. And in an infinite number of steps, we have only a set of points, an infinite number of points. Here the same. This is the cross fractal, and we have this cross will be repeated in this square, this, and we'll have this one. Then we repeat again, and this will be the third iteration, and all again this configuration. Okay. Now, for the other, I may have here. I have 2 and 3. It means that it is not necessary to have in each dimension to have the same number of subdivisions. Here I have 2 subdivisions times 3 subdivisions. Okay. Here I only remove this part, and now I repeat this C shape in these. Okay, and I have this is the Vic-sect fractal after some steps. This is another one. I can only remove the center, and then I have this drawing. Okay. This is you can see this as the face of the previous one, the face of this cube. Okay. If you think of repeating this process to this cube, we have this face after 1, 2, 3 iterations. Okay. This is the iteration of the cube, 1, 2, 3, 4 iterations, okay? You can find these drawings in the internet. These are lots of drawings of this type of. This is called Menger sponge. This is not quite a sponge, but it looks like, because this is a set of an infinite number of points, okay? Okay, we have these bisect fractals, okay? I just redefined, okay? This is x1 plus k1, x2 plus k2, and so on, xd plus kd. And now I will give this type of iterated Fourier systems as domains for this kind of systems. We have x and y non-empty complete metric spaces. X must be bounded, and p at least 2 be an integer. Let's have Fk, a family of injective and contractive functions, such that the union of these are x. And then we have another family of functions. In this type of function, we have 2 coordinates. And the second coordinates is for the phi dependence, okay? This will be the fractal dependence. Then, for this kind, there is an exact one-bounded function phi solution for this system. I will not go further the compatibility conditions, but there is the need to ensure that this will be fulfilled to have ensure that these kind of systems as solution. Okay, you may see it in my paper, compatibility conditions for systems of iterative functional equations. Okay, such a function, the solutions of this type of systems has fractal structure. This is well proved in the literature. Okay. And this system has p equations, and the unknown function and its domain may be obtained as an attractor of an iterative function system. Okay, the family of Fk, capital Fk, characterize the type of system: affine, double affine, nonlinear, and the simple case is the double affine. I call it double affine because I have the the dependence of fractal and the x dependence. These 2 types of dependence. That's why I call it double affine. Okay? The simple case, we have this iteration function system has the domain. Okay? And the elements of the domain are a P representation form. Okay, this is the P representation form of the domain. Okay, the double affine case, that is affine in both coordinates of capital F, is the most used case in the literature and corresponds to the system of iterative functional equations given by this. Okay, I call these coefficients fractal coefficients. Lots of papers in the literature call this also vertical factors, and these B are the directional coefficients. Okay, and this is the simple case where the P representation are given. Okay, the fractal coefficient must be in between a minus 1 and 1. Okay, such a function is usually called fractal interpolation function, and I call it now more recently, fractal regression function. Okay. The explicit formulation is given by this expression. For more general cases, you also may find it on my theoretical fundamentals, that is constructive solutions for iterative functional equations. You may find it in the literature. Okay. If some or one or more functions from this family are removed, then we'll have a Cantor-like domain to the system. Okay. For the generalization for a d-dimensional domain, we have the functional iteration function system described by this one. This is a fixed fractal type of domain. We may have the full d-dimensional, or we may have remove some of the coordinates, giving a fixed fractal. Okay. If you remove some, we'll have a fixed fractal domain. Okay, d-fixed fractal systems of iterative functional equations. We have a d-fixed fractal domain of the double affine case. I start with the simplest one case to study. Of course, this will be generalizable. I will do much work about this type of systems. Now, as K is a vector, X is a vector, then the Y is the same one scalar, but X is a vector. Then here, instead of being X a scalar, this will be a vector. Then B will be also a vector. Okay? Then we have here BK will be a vector here that and then the V-sect fractal system will be this. Okay? The V-sect fractal domain and the corresponding F, capital F of the system. Okay? This X will be a d-dimensional vector. The goal is now to extend the theoretical results obtained for one-dimensional case for the d-dimensional case in case of V-sect fractal. Okay, in particular the V-sect fractal system. In a matrix form, the double affine d-vector fractal system is given by this one. Okay, this is an easier way to write it down. Okay, we have d-dimensional X and d-dimensional BK vectors. The explicit solution now we can give the explicit solution by this, where here we have the matricial notation here, and here we have some sums and products to this. You see, the explicit solution depends on the representation of the d-V-sect fractal here. Okay. And let Ks be a d-V-sect fractal, and the phi unique solution, bounded solution of this system. Then these are the conditions. Then if we have P, the minimum of Pi, then in the case where we don't remove nothing, it means that S have all the indexes, then the Riemann integral of the graph exists and is given by this. The existence of this Riemann integral is very easy to understand because as we have here a domain that has is easier to obtain by is numerical, we can each time define each step by step where is the point. Then this is not, even if not continuous, is numerically countable. Is countable the number of the points of the domain, and this as is countable the Riemann integral may be obtained here. This is a generalization for the Riemann integral of the integral I computed for the basic case. Okay. These two kind of theoretical results are given, and my goal is to develop. Also, will be very interesting to me to develop my regression method. My method is for one-dimensional case, and this kind of structure will enable me to develop two-dimensional regression model. Okay, and I may give you some general reference about fractals. These are, for instance, explicitly defined fractal interpolation functions where I have explicit formulations for the solutions. Constructive solutions for system of functional equations are where there are theoretical formulations and the properties of this type of solutions, and then some basic references for fractals. Okay. I thank you very much for your attention, and now, if any questions or remarks.
Any Hausdorff dimension kind of things are there?
Hausdorff dimension. The Hausdorff dimension, yes, there is a Hausdorff dimension. I didn't put here, but the Hausdorff dimension is given by the solution of the sum of the contractor factor power S equal 1, and the S will be the Hausdorff dimension. This normally is an upper estimative. Okay.
And the matrix forming, like any importance about that matrix form?
The matrix the matrix is given to the domain of the system. Okay.
Or is there any important thing about that? Any result?
I don't. This is a starting point for my research. This is the first paper I prepare with Buescu and Luis, my collaborators. This is the first time I work with this kind of fractal object. This is a fractal function, and the domain will be also a fractal set. Very interesting because we have both a fractal domain and a fractal function, and this is a mixed in between the domain and the images. Okay.
So you mentioned about the research being in one dimension, right? So
Yes.
it's just plain one dimension. What about something like a 2D manifold, like let's say Klein bottles? it only makes it makes sense only in 4 dimensions per se. So in those cases, how will these iterative functions deal with these
For
systems?
for these systems, we must have a domain that that must be defined in some representative way. Okay, I have to have coordinates that may be represented each coordinate in a P representation system.
So even if this is a 2D manifold, I have to treat this as a 4-dimensional thing and then 4 coordinates and
You have
so on.
yes, you have to give each coordinate its representation and then have this is not. I cannot put any fractal in the domain. I have
No.
to be with a fractal that may be represented in this kind of interactive functional system.
So in this case also, dimensions when we are dealing with it, what kind of dimensions are we thinking of? Just Hausdorff or is it?
Hausdorff dimension. Normally, I can both. I can estimate the Hausdorff dimension of the domain, and I also may estimate the Hausdorff dimension of the images of this function. Yes, it should be yes, yes. Welcome. Easier way to compute the fractal dimension. The Hausdorff dimension is much more complex and difficult to obtain, and normally box dimension is estimative for the Hausdorff dimension. If I have already the box dimension, if I have already the Hausdorff dimension, I don't need to think about box dimension, okay? Any more questions?
I thank Dr. Cristiana Serba, University of Lisbon, Portugal, to accepted our invitation to deliver the talk in the ISMAFDS 2023, the symposium. Thank you, madam. And I thank the session chair, Dr. Guruprem Prasad from IIT Guwahati. Thank you, sir. Now I request Dr. Tanmay Som, IIT VHU Varanasi, to give the small token of memento to the Cristiana Serba. Thank you. Now I request Dr. Guruprem Prasad, sir. So certificate and conference. Thank you. Thank you, madam.